Okay, all right, now I'm going to record geometrical optics for you, and some of these it's going to be easier just to show you a picture of the answer than to try to actually work it because I can't draw very well on this little tablet that I have. But let's see what we can do here. All right, so it says here, oh, come on, cooperate. There we go, that a student performs an experiment to determine the index of refraction in of a rectangular glass slab in air. She is asked to use a laser beam to measure the angles of incidence in air and the corresponding angles of refraction in glass. The measurements for the angles for 5 trials are given below. All right, and then it says, complete the last 2 columns in the table by calculating the quantities that need to be graphed to provide a linear relationship from which the index of refraction can be determined. Label the top of each column. All right, so you're going to want to take the slope of the line. Okay, slope of the line. So here are the values that I had as being plotted. So here's my sine of angle I, and here's my sine of angle R. So all I did was punch 30 degrees in the calculator and get that, 40 degrees, 50, 60, 70, and then 20, 27, 32, 37, and 40 are these values right here. Okay? All right, then they ask you in Part B to plot a graph. Okay? So here is my sine I, and here is my sine R. And I plot this one on the x-axis because I'm controlling that by 10, 20, 30, 40, and so on. So that's why it's plotted on this axis. This is sine R, which is the corresponding refractive angle, the sine of the refractive angle that corresponds to the angle of incidence. So that's what that graph would look like. All right? Now realize that if you take the slope of that line, you're going to get rise, which is sine R, over run, which is sine I. Okay, that's kind of odd because n is equal to sine I over sine R. So when you plot it, and we'll talk about it in a minute, you're going to wind up with 1 over n. Okay, so don't worry about it. It's all good. All right, so let's get rid of that. Let's go on back here. So that was our graph, all right. And then it said, using the graph, calculate the index of refraction for the glass slab. So I just drew myself a best fit line. And then I took the slope of that best fit line. I didn't use the points that were in the data table. I actually took the slope of that line. So when I did that, let me find my answer in my work over here. I said that I had a rise and a run, so I'll show you what my rise and my runs were. Okay, so I had a rise, and when I plotted that, I used, I wrote them down, 0.56 minus 0.34. So my rise was 0.22. And then my run, I said was 0.83 on the x-axis minus 0.48. And that gave me a run of 0.35. So the slope of that line is equal to 0.22 over 0.35. And when I did that, if I wrote it down, which I hope I did, I got 0.06, way to mess up, 0.62875. All right, but this was the sine of R over the sine of I. Well, I know that the index of refraction is sine I over sine R. So what that tells me is that this value right here is really the same thing as 1 over n. So if I took n and divided 1 by 0.62875, that would give me the index of refraction. And when I did that, I got 1.6. So sometimes when you take the slope, you have to mess around with it to get the value that you want. Okay? So if you're confused, pause it, reverse, and go back. It's not real bad, but you got to understand what's going on there. All right, so let's scroll on down. Oops, doop doo doop doo doop doo. Okay. So the next thing that it says is the student is also asked to determine the thickness of a film of oil on the surface of water. Light from a variable wavelength source is incident vertically on the oil film as shown above. The student measures a maximum of intensity of the reflected light when the incident light has a wavelength of 600 nanometers. All right, so let's take a look at what's going on here. So this index of refraction is 1.0. The oil itself was 1.43 and the water was 1.33. So remember, you had to talk about hard bounces and soft bounces. If it went from a lower index of refraction to a higher index of refraction, we said that was a hard bounce and it went out of phase by 1/2 of a wavelength. If it went from a higher value to a lower value, we said that was a soft bounce and that it did not change phase when it did there. And it said, so at which of the two interfaces does the light undergo a 180-degree phase change on reflection? So that happens when it tries to move from the air to the oil, because that's a hard bounce. This is a soft bounce, so there is no phase change there. Okay? All right. Let's move on. Calculate the minimum possible thickness of the oil film. All right, so I said, well, I said that it had to go down and come back up, so that was 2T, twice the thickness, all right. And so I said that the wavelength of the film, wavelength of light in the film was equal to the wavelength in the air divided by the index of refraction for the film. So the wavelength of our light in air was 600 nanometers. Our index of refraction for our oil is 1.43. So when I divided those, I got 420 nanometers. All right, and then I said, okay, well, twice the thickness is equal to, because I'm looking for that hard bounce, lambda over 2. So the thickness would be lambda over 4. So that's 420 divided by 4, or 105 nanometers, is the thickness of the film. Okay? All right, so that wasn't too big of a deal. All right, let's go on to the next one. Yeah, we got a few more minutes. Okay. So then I'm going to pause for a minute. All right. So this next one says, the concave mirror shown above has a focal length of 30 centimeters. You're given a candle 5 centimeters tall. You wish to produce an image on a screen that has a magnification of -3. State whether you would... come on, I don't have time for this. There we go. State whether you would place the candle on the left side or right side of the mirror shown above and explain your choice. So there's what's going on. You better put your candle over here, because this is where your shiny stuff is that's going to do your reflecting. So I would put it on the left side, and I would tell them that I knew that the concave mirror has the shiny surface on the left-hand side. So if I wanted the light to reflect, I needed to put my candle right there. And that's supposed to be a candle flame. Okay. All right. Okay, then it says, Part B says, choose an appropriate object distance for the candle and calculate the corresponding distance from the mirror at which the screen should be placed in order to see an image 15 centimeters tall on the screen. Okay, so I said, well, if you want the image to be enlarged and you want it real so that it'll show on the screen, you need to place the candle between F and 2F. And I know that because I've studied the ray cases. All right. So then I said, well, 1 over di plus 1 over do equals 1 over F. And so I said that 1 over di plus 1 over do, well, I just picked 40 because I knew that was between 30 and 60, is equal to 1 over 30. And so when I did that, I got di to be 120 centimeters. Okay. All right. So we did that. Okay. Let's move on. All right. Part C says to draw a ray diagram. Well, I can't draw a ray diagram because I can't even, there's no way I can get a straight line. So let's look at this and see what this shows us. So here is the ray diagram. So there's where my image is formed. Goes in parallel out through F. This one is just going to go through the center curvature of the mirror. And that's where my image is going to be formed, right in there. Okay. Alright, so we pretended I drew a ray diagram. And then we were done with this one. Alright, so let's wrap it up. Okay, so this one says light of frequency 6 times 10 to the 14th hertz is coming up through the glass, hitting the air, and then going back. Alright, partially reflected, partially refracted at the boundary as shown above. Index of refraction for glass is 1.6. Alright, so they want to know what is theta 3 if theta 1 is 30. So the law of reflection says that the angle of incidence has to equal the angle of reflection. And you can't just put angle R because they might think that you were talking about angle of refraction, so be careful there. Determine theta 2 if theta 1 is 30. So N1 sine theta 1 equals N2 sine theta 2. So N1 is my glass, sine of 30. N2 is my air, sine of theta 2. So when I popped all that into my calculator, I got a lovely value. And my lovely value that I determined was 53.1 degrees. Theta 2 is 53.1 degrees. So that's my answer for B. Alright. And then I went on to C, D, and E. So C said determine the speed of light in this glass. So I said, well, N is equal to C over V. So B is equal to C over N. So 3 times 10 to the 8th over 1.6 gave me a value of, well, when I did that, I got 1.88 times 10 to the 8th meters per second. Alright, find the wavelength. Wavelength in glass is going to be speed over frequency. So 1.88 times 10 to the 8th meters per second over frequency. They told us the frequency was 6 times 10 to the 14th hertz. So I got the wavelength in the glass to be equal to 312.5 nanometers. And then they wanted to know what is the largest value of theta 1 that will result in a refracted ray. So they're asking you about the critical angle. They want you to send it up like that and then have it refract along the boundary between the two. So if you remember what we did with that one, we said N1 sine theta 1, N2 sine theta 2. So this was going to be our 1.6. We're looking for theta 1. Air is always 1.0. Sine theta 2, it's going to refract at a right angle. Here's your normal. You're going to measure that angle right there. So sine theta 1 is simply going to be 1 divided by 1.6. So when I did that, I calculated theta 1, and I got 38.7 degrees. So that's the critical angle for that piece of glass. Woo, we got through those. All right.